Okay, so looking at the inverse square law, so essentially it's saying because of the 1 over r squared relationship that it reduces in an inverse square. That's pretty much all you need to know. How does it vary from the Earth's centre? So G, how does it vary as you go out? Okay. Remember, it's going to decrease as you go out, going in this sort of relationship. If you think about what G is equal to, it would be Gm over r squared. Okay, so it's definitely going to go to the 1 over r squared. This one here is talking about actual gravitational potential, which is phi, which is a bit later on, which is actually Gm over r negative, and that's why it's actually a 1 over r relationship. This is probably a better representation of G. Okay, so at the surface of the Earth, you can see there it's 9.81. Okay, down towards the centre it's 0 essentially because you've got equal amounts of mass pretty much on each side pulling against you, so you cancel out to make 0. Satellites, well, these are quite interesting. So if you think about a satellite going around the Earth, okay, so there's your Earth, there we have a little satellite, and that would go around Earth in a circular fashion. Okay, now there's only one force on the satellite itself, okay, and that's the gravitational attraction. Okay, so the weight, and you could actually say that there's an equal and opposite weight from the Earth. Okay, but the weight here is the only one on the satellite. Now, because it has a forward velocity, then it can go in a circular motion, and so something that tells us about that circular motion will be that mv squared over r is equal to its weight. Now, how can we actually calculate its weight? Well, you could actually use F equals Gm over r squared. So if we put that in here, G, m for the Earth, m for the satellite, divided by r squared, is going to be equal to mv squared over r. Now what you can do is you can simplify all that, and maybe solve it for v. So v equals square root Gm over r. Okay. What's interesting about this is it doesn't matter about the mass of the satellite. It only matters about if you want to be in a particular radius, so you want to be in that radius, then you have to be going at some particular velocity. If you increase your velocity, then you must have to change your radius. But it doesn't matter what mass you're at. So if you've got all your satellites at a certain distance travelling around the Earth, okay, it doesn't matter what mass they are, they just all have to be going at the same velocity. It's quite handy because they don't then crash into each other. What will happen when the satellite speed is increased? So if you've got the equation v equals square root Gm over r, okay, if you increase this side, then theoretically the other side has to increase as well, so you need to decrease the radius because the other two are constants. So that sort of makes sense, but if you actually think, and the equation makes sense, but logically you think about it, you think that if you did actually increase the velocity, would you not go into a wider orbit? And effectively you do, okay? So it's quite difficult to think about what's happening there. But essentially, if you increase your velocity, you are keeping the same gravitational pull at that time, and so it's not going to be able to handle the mv squared over r. So if you increase your velocity, then your weight, which is fixed at that distance, cannot handle the v squared, okay? So it stays the same. So at that time, if you increase the velocity, then you must also increase the radius. However, if you want to then be at a larger radius later on, so a larger radius, you then need to have to slow down to a slower velocity. What happens when the radius of the satellite's orbit is decreased? How do we decrease it? So that's essentially what we just talked about. We now want to decrease this, so you must decrease your velocity because your weight is fixed. Okay, and then once you've decreased your orbit, so we're going around orbit, we're going to decrease to a new orbit. You then need to do this one here. We've now decreased the radius, you now need to increase the velocity. So you slow down and then you want to speed up so that you can go in that orbit. If you're on a satellite, it is just like free falling towards Earth, okay? Because essentially if you throw an object, it'll follow a parabolic path. Throw it far enough, then it could actually go in a circular path around the Earth. Okay, you need to throw it very fast. So effectively, it is falling towards the Earth. So imagine the satellite is falling towards the Earth, but the Earth is falling away at the same rate as it goes around in a circle. So this is what we do here with these planes to sort of model the effects of no gravity. The planes fly up high, and effectively they then sort of go in a parabolic motion that will follow the parabolic motion of the humans inside, and so they don't actually have to touch the walls physically to actually stay inside the plane. You know, they don't need to be sitting down to go with the plane. The humans are in the same parabolic motion as the plane, and so they can actually just move around. It's just like going over a bump in a car. You get that butterflies feeling because you no longer need the car to travel around the bend. You're just going around with centripetal force equal your weight. And your guts inside also feel the same thing, hence why it might not feel very good. So at what speed must a satellite be travelling so that it can remain in circular orbit 1600 kilometers above the surface of the Earth? Well, you could just use that. You're supposed to write Fg is equal to the force centripetal. Okay, so mg over r squared equals mv squared over r. And you can solve for an equation which we just talked about before. So v equals square root g m over r. Substitute into that. You'll find it'll be pretty quick. Gravitational potential. Gravitational potential at a point is gravitational field. It defines the work done in moving unit mass from infinity to that point. So phi, change colours. Phi is equal to the work done in moving a mass from infinity to that point. Okay, so per unit mass. Oh yeah, whoops. Sorry, I did have that there. It's there. So work done per unit mass. Okay, so what's your unit? Well, it's work per unit mass.